We are now going to take a look at a situation for an object on an incline where the object is accelerating. In this particular case, our 7-kilogram turkey is on a hill with an incline of 30 degrees. This time, we are given a coefficient of kinetic friction, and we are assuming that the turkey is going to begin sliding down the hill. The problem asks us to determine the acceleration of the turkey. How do we go about doing this? Well, as always, a good starting point is going to be a free body diagram. In this particular situation, I'm going to draw my incline. We have a 30-degree angle, and if we put our object, the turkey, on the hill, I'm going to establish my x-axis along the slope of the hill and a y-axis perpendicular to that. We will call that the positive direction, and down my y-axis negative. I will call up the slope negative, and I will call down the slope the positive x direction. For my forces, I'm going to add in, as we did in previous problems, a weight force or force of gravity going straight down, a normal force that is perpendicular to the surface, and a kinetic friction force working against the motion of the turkey. These are the only forces that will be acting on our turkey while it begins to accelerate down the hill. Now what I want to do is apply Newton's second law. We're going to say that the sum of the forces on our y-axis is 0 because the turkey is not accelerating in the positive y direction and it is not accelerating in the negative y direction. We're also now, what we're going to do now is take a look at the forces on the x-axis, where we will have the kinetic friction force, which will be working against a component of gravity. And so, to keep moving here, what I need to do next is take a look at the force of gravity, which is in between my x-axis and my y-axis, and I need to separate that into components. To do that, I'm going to say the force of gravity, redraw it here, with my axes. There's the y, there's the x. I'm going to draw my y-axis component first, so there is the force of gravity on the y-axis, and then making sure that this next component is perpendicular to the y-axis component, I'm going to draw the x-axis component of the force of gravity. If we now take a look at the sum of the forces on the x-axis, it's going to be the force of gravity on the x-axis added to the negative direction kinetic friction force. I also know from breaking my gravity into components that the normal force will be added to the negative direction force of gravity on the y-axis in this particular situation. Now, we are simply looking to figure out the acceleration here. By Newton's second law, we are going to say that the sum of the forces is equal to the mass of our object times the acceleration. Since there is no acceleration on the y-axis, we can say that the sum of the forces is only going to be the sum of our x-axis forces and if I can figure out the sum of the forces on the x-axis, since I have my mass, I can now solve for acceleration. Going back to what we had done earlier, I can solve for both force of gravity on my x-axis and the force of the kinetic friction force using physics formulas. Previously, we had shown that the force of gravity on the x-axis would be equal to m times g times the sine of theta. If you could not remember that, however, keep in mind that the reason I knew that was because this angle was congruent to the incline of the hill, and if this is 90 degrees, then I know that this is the opposite side of my angle, and this is the hypotenuse, and I'm just simply using the sine function in SOHCAHTOA to figure out what my components are. Next, I also know that the kinetic friction force is equal to mu k times our normal force. Since I know mu k, all I need is the normal force in order to solve for the kinetic friction force. Now, in this particular case, normal force, as we showed earlier, has to cancel out with the force of gravity on the y-axis. So, if I can figure out the force of gravity on the y-axis, I will know the size of the normal force. And once again, from what we had learned yesterday, the magnitude of the normal force is going to equal the magnitude of the force of gravity on the y-axis, and we can calculate that by doing mg cosine theta. I'm going to take this value and I'm going to substitute it in for my normal force, and that will give me a kinetic friction force equal to mu k times m times g times cosine theta. Now, since I have Fk and I have Fg on the x-axis, I can go back to the sum of the forces on the x-axis from earlier and solve for the sum of the forces on the x-axis. That's going to give me for the force of gravity on the x-axis, mg sine theta, and I'm going to, mg sine theta, and then I'm going to be subtracting the force of friction, which we just figured out to be mu k mg cosine theta. Now, you can factor out m and g here if you would like, and there are some other algebra things you can do, but we do now know enough in this problem to solve for the sum of the forces on the x-axis. The problem gives us the mass, we know g, we're given an angle, we know the coefficient of friction, and we know m, g, and theta again, so we should be able to solve for the sum of the forces on the x-axis. Now, without plugging numbers in yet, however, I'm going to solve this, set this equal to and do mg sine theta minus mu k mg cosine theta, the sum of my forces, equal to mass of the object times the actual acceleration of the object. And a nice thing happens here algebraically. Our masses, which we find in each term, are going to cancel out with each other, and we're able to solve for the acceleration without having a value for the mass, which should make sense to you because we know from previous units that the mass of the object should not affect the acceleration it experiences due to gravity. So, plugging in some numbers now, we're going to have 10 meters per second squared times the sine of, I need to remember what my angle was here, 30 degrees. Minus mu k, which we have as 0.10 times 10 meters per second squared times the cosine of 30 degrees equal to the acceleration